Namaste bachcho. Welcome. Today we're going to study a very interesting topic from our current electricity unit, the resistivity of various materials. Now I know this is a topic where many students get confused, but don't you worry. This idea is super important, and after this explainer, I promise you will understand it so simply you'll remember it for your entire life, and it'll be completely exam safe.
Okay, so let's start with a simple question you see every day. Have you ever wondered, the copper wire that brings electricity to your toaster, it just stays cool, na? But the wire inside the toaster itself, it glows red hot. They are both just wires, right? So what's the difference? The entire answer, bachon, lies in one single property, resistivity. And we are going to understand it today with a very simple analogy. Right, so before we jump into all the complex physics and formulas, let's just build a strong intuition first. Let's get a feel for it. Just imagine we have to evacuate a big stadium. How easily and how quickly this happens depends on the stadium's design, isn't it? Well, this is exactly like how easily current flows through different materials.
So first up, let's look at a conductor, like our copper wire. Think of it as a massive stadium, and it's completely packed with people. These people, they are our free electrons. And look, there are hundreds of wide open exits. So when the signal is given to evacuate, it's super easy, fast, and very orderly. This is exactly why current flows so easily through copper. There are tons of free electrons ready to move, and very few obstacles.
Okay, now let's move to our next case. What about a semiconductor, like silicon? Well, a semiconductor is like a stadium that is almost empty to begin with. See? There are very few people, which means very few free electrons. And the few exits that exist are very small, so only a small trickle of people can get out. The flow is possible, but it's very limited. And finally, we have insulators, like the rubber coating on a wire. An insulator is like a stadium with absolutely no people inside, and all the exits are locked and bolted shut. So no matter what signal you give, no one can get out, because there's no one to move in the first place. No people means no free electrons, so no current can flow. It's as simple as that, right?
Okay, so that analogy gives us a great mental picture. It's a great way to start. Now, let's connect this story to the actual physics funda that you need for your exams. The property we've been talking about is called resistivity, and its symbol is this Greek letter rho, which kind of looks like a cursive P.
Now, here is the formula for resistivity. I know, it might look a bit scary at first, but don't worry, we'll break it down together. It's really simple. Rho equals m divided by n times e squared times tau. Now here, m is the mass of an electron, and e is its charge. Both of these are constant, so they don't change from material to material. The really important parts, the ones that make materials so different, are here in the denominator, n and tau.
So, the crucial point is that you only need to focus on our two heroes, n and tau, or tau. Now, n is the number density of free electrons. That's basically the number of people in our stadium analogy. Simple. And tau is the relaxation time. This is just the average time an electron travels freely before it collides with an atom. In our stadium, it's like the average time a person can run before bumping into someone else. Now look very carefully, bachcho. Both n and tau are in the denominator. That means if the number of electrons n is very big, or the free time tau is very long, then the resistivity rho will be very small.
And this table just brilliantly shows the difference. Just look at the numbers on this table. Look at copper. Its resistivity is just 1.7 times 10 to the power of -8 ohm meters. That is a tiny number. Now look down at rubber. Its resistivity is more than 10 to the power of 15. The difference isn't just a little bit, it is mind-bogglingly huge. It spans over 20 orders of magnitude. It's just an unbelievable difference.
So the big question is, what causes this massive difference? Well, it all comes back to our two heroes from the formula. N, the number of available charge carriers, and to some extent tau, the time between their collisions. Let's see how. It primarily comes down to N, the number of free electrons. In metals like copper, N is massive. We're talking about 10 to the power of 29 free electrons per cubic meter. It's a sea of charge. And because N is in the denominator of our formula, a huge N means a tiny resistivity. Now in insulators, the electrons are held very tightly by the atoms, so N is almost zero. With N so small, the resistivity becomes astronomically high. And then there are semiconductors, which are in the middle. They have very few free electrons naturally,
But, and this is the most important part for all of modern electronics, we can actually control this number n. Okay, let's make this feel real. You know nichrome, right? It's the material that's used in your toaster wires and heaters. So if we take two wires of the exact same length and the exact same thickness, one made of copper and one of nichrome, how much more resistance do you think the nichrome wire has? Just take a wild guess.
59 times. Can you believe it? For the exact same size, the nichrome wire has almost 60 times more opposition to the flow of current. And that is exactly why it is perfect for heaters. It fights the current, and that fight generates a lot of heat, which makes it glow red hot. Copper, on the other hand, with its super low resistivity, it just lets the current pass through very easily, without putting up a fight.
All right, now let's talk about some common traps, some ideas that sound correct but can actually make you lose marks in your exams. Let's make sure you have the correct exam-safe concepts locked in your mind.
So, a very common mistake is to think that semiconductors are just bad conductors, somewhere on a simple line between metals and insulators. No, that is not correct. The exam-safe concept is that they have a fundamentally different way of conducting electricity. It is not about being a weak metal, it's all about having a very low number of charge carriers, N, which we can actually control. This is a totally different kind of physics.
And here's another one. Some students think insulators don't conduct because their electrons are very slow or they get stuck. This is also wrong. The real reason, the one you absolutely must write in your exam, is that insulators have almost zero free electrons to form a current. It's not about the speed of the electrons, it's about their very existence as free charge carriers. Remember our empty stadium? No people, no flow. Simple.
But your understanding this correctly is super important because it connects directly to our next topic. When you change the temperature of these materials, something absolutely fascinating happens. In metals, temperature mainly affects tau, the collision time. But in semiconductors, temperature mainly affects N, the number of carriers. And this is why they behave in completely opposite ways when you heat them up. We'll study that next.
So let's just quickly revise the key takeaways from today. Point 1. Resistivity, ρ, is the material's natural inbuilt opposition to current. 2. It all depends on our two heroes, the carrier density N and the collision time tau. 3. Metals have a huge N, which is why they have a very low resistivity. 4. Insulators have almost zero N, which makes their resistivity extremely high. And finally, this single property is what determines a material's entire purpose in our world. So the next time you see a simple wire or a heater, I want you to remember the incredible physics that is happening inside. Think about it. What other everyday objects can be explained by this amazing property?